from UST Technology Malaysia. So for today, I'm going to present the project entitled Fabrication of Bioplastic from Project Permanent with Value Added Properties. Okay. So usually I will start my presentation with acknowledgement because without them, there will be no project. First of all, I would like to acknowledge my undergraduate students, Eylül, and also Eylül for conducting the project. And also these two companies, Lada Project Sunamberhad and also Capital Plus, for contributing the material for the project as well as the funder, UST Technology Malaysia. Okay. And this is the presentation, the overview of my presentation, where I'll start my presentation with background study, followed by methodology, findings, and lastly the conclusion. Okay, now, what is single-use plastic? So single-use plastics, plastic product that is used for only one time, and then it is discarded. And they are commonly found in food packaging and also straws for protection and preservation. And plastic are usually made up from petroleum base, and they are non-biodegradable. So because of this characteristic, plastic are the major contributor to municipal solid waste. And now, currently, the industry is shifting towards using sustainable alternatives such as bioplastic because they are more eco-friendly, compostable, and also biodegradable. So the sources for this bioplastic are usually made from plant fiber. Right. In this project, we are using the same plant as Prof. Shadidas presented before this, Amorphophilus mulleri. So I'm not going to explain in detail about the plant. And the plant is mostly found in Southeast Asia, and it produces one type of polysaccharide called glucomannan. And this glucomannan, it has the characteristic of it is able to retain water, and also it has the ability to form film. So that's why we think that it is suitable to become the sources for the bioplastic as alternative for the conventional plastic packaging. Okay. Previously, there have been research conducted by using Amorphophilus konjac glucomannan. So Amorphophilus konjac glucomannan is a different type of Amorphophilus species, whereas in our project we are using the Amorphophilus mulleri species. Okay. Based on the previous research, this glucomannan, this polysaccharide, they have to be blend or add with other types of materials because of their high water absorption characteristics. So based on the previous research, this glucomannan have been added with mung bean starch, chitosan, cassava starch because to improve its strength and also to improve its strength as a bioplastic. So we also found that based on the previous research, they add the glucomannan with beta-cyclodextrin to improve its thermal stability and also to lower down its moisture content. Okay, and so based on the previous study, we found that the addition of beta-cyclodextrin will help to improve the water retention of Amorphophilus species bioplastic, and most of the study come from Amorphophilus konjac glucomannan, which is different from the plant that we are using. And also we found that even though there have been many research about the bioplastic, but there are lack of study on the anti-ripening study of the Amorphophilus species from the bioplastic. Okay, so in this project, what we do is we try to use the glucomannan from Amorphophilus mulleri, where we add it with different types of polysaccharides such as beta-cyclodextrin, agarose, pectin, amylopectin, chitosan, and sucrose acetate to determine what is the best formulation to produce the bioplastic, and then we add it with glycerol, which is a plasticizer to improve its flexibility, and also chitosan as the anti-ripening agent. And then we do the characterization, FTIR, some swelling degree analysis, water solubility analysis, and also tensile strength analysis. And lastly, what we do is we do the anti-ripening task on calamansi. Okay, so from the findings, at first what we do is we have to test whether this type of Amorphophilus species able to produce bioplastic or not. So what we do is we test the glucomannan itself without the addition of any polysaccharide, and yeah, the glucomannan able to produce to form film, but then after we add the film into water, the bioplastic disperse. It becomes soluble in water. So meaning that we have to add the glucomannan plus bioplastic with some other polysaccharide. So here we try it with different types of polysaccharide, and the final or the best formulation that we get is by the addition of glucomannan, and then with the addition of beta-cyclodextrin and also cellulose acetate. So what we do next is we proceed with this formulation, and we also do surface morphology analysis and also functional group analysis to determine the best to validate the result. So here we found that with the addition of glucomannan, beta-cyclodextrin, and also cellulose acetate, the surface of the bioplastic, it has a high granule structure, where this structure it will help to retain or trap a large amount of water, and also from the FTR analysis, the bioplastic has this highest strategic vibration of the functional group of ester carbonyl, carboxyl, and isoaminoous unit that will provide a stronger interaction between the polysaccharides, where it will become a more flexible polyplastic. And we also do some water soluble analysis, swelling degree, and also tensile strength analysis. Here it shows that when we add the glycerol as the plasticizer, it helps to maintain the film when we add the film, or when we add the bioplastic in water. And also when we do the tensile strength of the bioplastic that we have is 0.29 megapascal, meaning that it falls under the normal plastic strength, tensile strength. So meaning that we can use this as a bioplastic, as a plastic, or as a food packaging. Okay, and then we do some morphology analysis back, because after we add the glycerol, so we just want to know what will happen. What happened to the surface of the material, and we found that it still has this granular structure, but then the granular structure has become more homogeneous, and this homogeneity helped to improve with the mechanical strength, where it become more. We can stretch it more, the bioplastic, and then we proceed with the anti-ripening test. We test it on the calibracy or small line, and we use different types of nanochitosan with different ratio. Here we test it with chitosan and also nanochitosan, and we found that with the addition of nanochitosan, it helps in slowing down the ripening and also the softness of the fruit. Okay, so lastly, as the conclusion, we managed to get the bioplastic from the Amorphophilus mulleri plant with enhanced water resistance and decreased water solubility, and also with the addition of nanochitosan, it able to decelerate the ripening process, and also still maintain the fruit in a good condition even after 3 days. So basically, we can use glucomannan from Amorphophilus mulleri as alternative resources to produce a bioplastic. Okay, so with that, I thank you. I don't know how to pronounce thank you in Turkish.